So our topic for today is the power series of this equation, y double prime plus y is equal to 0. So first, let's define y in its power series form. So it is the summation of n is equal to 0 to infinity times c sub n times x raised to n. So y prime is equal to summation of n is equal to 1 to infinity times n, the derivative of this, cn x raised to n minus 1. So y double prime is equal to summation from n is equal to 2 to infinity n times n minus 1 times cn c sub n times x raised to n minus 2. So rewriting this using this power series will give us this. C sub n x 2 plus summation of So in order to evaluate this, we need to factor out x raised to n and its summation. So in order to do that, let's move this n to the left, and by moving that, we should add plus 2 here, since we will get 2 from here. So our new equation would be like this. X raised to n minus 2 plus 2 is x raised to n, and we'll just copy this. So now we can factor out the summation and x raised to n. So it will be like this. X raised to n Okay. Here. So in order to evaluate this power series, you should remember that x raised to n must not be equal to 0. So this is now our equation. As x raised to n is not equal to 0, we can only equate this expression to 0. So what we'll get there is the recursion relation. So let's rewrite it. So in order to evaluate this, we transpose this to the other side and divide both sides by this. Why did we do this? Because the higher term or the next term depends on its previous term. As you can see, this is n plus 2 and this is only n. So our next step, by the way, this is what we call the recursion relation. So the next step would be solving for its values in order for us to evaluate it. So at n is equal to 0, C2 is equal to negative C0 all over 0 plus 2, 0 plus 1, 2 times 1, or negative CO over 2 factorial. At n is equal to 1, C3 is equal to negative C1 all over 3 times 2, or negative C1 over 3 factorial. At n is equal to 2, this is C4 is equal to negative C2 over 4 times 3. But as you can see, this is C2, we can get this here. So plugging that in here would give us CO over 4 factorial. At n is equal to 3, C5 is equal to negative C3 over 5 times 4. And C3 is here, and we plug this in here, would give us C1 over 5 factorial. Okay, at n is equal to 4, C6 is equal to negative C4 over 6 times 5. It's also equal to, plugging this in here, would give us negative CO over 6 factorial. At n is equal to 5, C7 is equal to negative C5 all over 7 times 6. And plugging this here would give us negative C1 over 7 factorial. Our next step is to get the formula for this to evaluate its power series. Okay, so if you see the pattern here, CO and C1 is alternating per n as it increases. So if n is equal to 0 and 2 or 4 or even numbers, it is C0. So at C2, and this is represented by even numbers. So this is CO all over. As you can see, it's also at even numbers. This can also be represented by 2n factorial. Another thing, look at the sign. It is also alternating. At n is equal to 0, it is negative. N is equal to 2, it is positive, negative, then positive. So you can represent it by multiplying it by negative 1 raised to n. Okay. So now let's move on to odd numbers. This is represented by odd numbers. If this is CO, this is C1, and following by its pattern gives us this. It's also the same in terms of its sign, so we multiply negative 1 raised to n. So since we got the formula of our recursion, I'll teach you something. So C0, C1, C2, C3, C4, C5, power series x raised to n. Remember, we have x raised to n outside the recursion relation. So as this increases, this also increases. X raised to 0, x raised to 1, x squared, x cubed, x raised to 4, x raised to 5th. And this is even. And this is odd. Okay, so we'll use that later. Actually, right now. So if this is for even numbers, remember, and this is for odd numbers. So plugging in 0 here would give us C0 over 2 times 0, 0 factorial, negative 1 raised to 0 is 1. It will give us C0. Okay, so plugging this term, plugging 1 into this n, it will give us C2 is equal to C0 all over 2 times 1 is 2 factorial times negative 1 raised to n. So that would be negative CO over 2 factorial. Okay, next is plugging 2 here, so that would be C4, and then C0 over 4 factorial times negative 1 squared, so that would be 1. Okay, so plus C0 over 4 factorial. Okay, minus that. Okay, remember what I have told you here. So this is C0, right? C0. So that would be x raised to 0 times 1. And this is C2. As you can see, there is x squared there. C4, x raised to 4. We can factor this out. This is C0, 1 minus x squared, 2 factorial, plus x raised to the 4th, 4 factorial, minus that. And let's this series of equation, this is a transcendental function. This is actually cosine of x. Okay, so now we move on to the odd numbers. So C2 times 0 plus 1, plugging in 0 again from 0. Okay, so this is C1 is equal to C1 all over 2 times 0 plus 1, so 1 factorial. C1 over 1 factorial raised to 0 is this. C1 over 1 factorial. Okay, the next one, plugging in 1, it would be C3 is equal to C1 over 3 factorial times negative 1 raised to 1. So that would be C1 over 3 factorial. Okay, let's plug in 3. So this would be C5. It would be equal to C1 over 5 factorial. And this would be squared. This would be 1. So that would be C1 over 5 factorial minus that. Okay, factoring this out again. C1. Okay, wait. Remember this is C1. Our x here is raised to 1, so let's put x here. This is C3 x cubed. C5 x raised to 5. So let's factor that out. Now we're left with x minus x cubed over 3 factorial plus x raised to 5 over 5 factorial minus that. And if this is cosine x, this is sine x. Okay, so final answer would be CO cosine x plus C1 sine x. So our next problem would be y double prime minus y is equal to 0. So learning from our previous lesson, we get the power series of y and y double prime, substituting it back here. So we're given of this, and for us to evaluate this, we need to factor out x raised to n and the summation. So in doing that, we move this from 2 to 0, and we added plus 2 on each n here. So doing that and factoring the summation from n is equal to 0 to infinity and x raised to n would give us this. So remember, x raised to n must not be equal to 0. So our recursion relation would be, we would get it from here. So rewriting that would give us this, and according to our previous problem, simplifying that would be transferring this cn plus 2 equals cn all over n plus 2 and plus 1. So this is now our recursion relation. So now this is our recursion relation. So let's plug in values. At n is equal to 0, this is c2 is equal to c0 over 2 times 1. So this would be co to factorial, and at n is equal to 1, c3 is equal to c1 over 3 times 2, or c1 over 3 factorial, and at n is equal to 2, this would be c4 equal to c2 over 4 times 3. Plugging c2 in would give us co over 4 factorial. So at n is equal to 3, c5 is equal to c3 over 5 times 4, plugging in values there, and c3 would be c1 over 3 factorial, so this would be c1 over 5 factorial. So our next step would getting the formula of this. So according to our previously from our last problem, as you can see, CO and C1 is alternating. CO is within the even numbers, and C1 is within the odd numbers. So at even numbers, it is CO, and this also at even numbers. So if this is 2n, you write here 2n factorial. Okay, at odd numbers, C sub 2n plus 1 is equal to C1 all over 2n plus 1 factorial. It's easier than the last. So this was our formula. What we're gonna do now is plugging in values. So plugging in 0 here, 2 times 0 is C0 is equal to C0 over 1, 2 times 0 is 1 factorial, 0 factorial is equal to 1, or 1, so plus, plugging in 1 here, be C2, so C2 has x squared, and C0 all over 2 factorial, plus C0 times, plugging in 2 here, C4 is x raised to 4 factorial, plus dot, and simplifying this would give us CO times 1 plus x squared over 2 factorial plus x raised to the 4 factorial, plus dot. This is also equal to hyperbolic cosine of x. Okay. Plus, let's solve for this. Plugging in 0 here would give us C1. C1 has x, so C1x all over 1 factorial, plus plugging in 1 here would give us C3. C3 has x cubed, C1 all over 3 factorial, plus C1, and plugging in 2 here is 5. So C5 has x raised to 5th over 5 factorial, plus dot is also equal to C1 times x plus x cubed over 3 factorial plus x raised to the 5th over 5 factorial plus dot dot dot. This is also equal to hyperbolic sine of x. So our final answer would be C0 cosine hx plus C1 sine h of x. There. Okay, so for the last example, is y double prime is equal to 4y. So before that, let's get this y and y prime in its equivalent power series. So this is from the previous lesson, and plugging in those values here would be this, and what I did here is to transpose here this into the other side. Then for this x raised to n, and the summation, for us to factor it, I move this to the left so that this we will add 2 to all the n here, thus having x raised to n here. So in here, as you can see, you can factor out the summation and x raised to n. So here is our new expression, and as x raised to n should not be equal to 0, so we equated this into 0 and forming our recursion relation. So for the next step, after getting the recursion relation, we would plug in values at n. So at n is equal to 0, this would be C2, 4, C0, 2 times 1, or 4CO over 2 factorial. At n is equal to 1, C3 is equal to 4 C1 over 3 times 2, or 4 C1 3 factorial. At n is equal to 2, C4 is equal to 4 CO over 4 times 3. Oh, sorry, this should be C2. And C2, as we know, is this, so this is 4 squared CO over 4 factorial. At n is equal to 3. This C5 is equal to 4 C3 all over 5 times 4. And plugging C3 here would give us 4 squared C1 all over 5 factorial. And at n is equal to 4, C6 is 4 C4 over 6 times 5. This is 4 cubed. Plugging that to here, 4 cubed C0 all over 6 factorial. And at n is equal to 5, C7, 4 C5, 7 times 6. Plugging this in would give us 4 cubed C1 all over 7 factorial. So for the last part, we will get the formula for this one. So as you can see, similar to our previous examples, the CO and C1 is alternating for even and odd numbers, as well as its denominators. So for C raised C2n, even numbers, equal to CO all over 2n factorial. Since now we have a constant here, and it is increasing as n increases. So put here 4 raised to n. At even numbers, c2n plus 1 is c1 all over 2n plus 1 factorial times 4 raised to n, as it is similar to the even numbers. Okay, so now let's evaluate the values so we get y. So let's start at even numbers. If this is 0, c sub 2 times 0 is 0, c0 equals c0 over 0 factorial 1, and 4 raised to 0 is 1, so this is c0. Okay, so if this is 1, c sub 2 times 1 is c2, so there should be x there, x squared equals c0 all over 2 times 1 is 2 factorial there. Now next c0, 2 times 2 is c4, so there should be x raised to the 4th there, 4 factorial times 4 squared. Sorry, this should have 4. Okay, plus dot, and let's factor this out. c0 1 plus x squared 4 all over 2 factorial plus CO, oh joke, 4 squared x raised to the 4th over 4 factorial plus dot. So for the next one, plus for the odd terms, at n is equal to 0, this will be c1. So c1 has x there all over 2n plus 1 should be 1 factorial times 4 raised to 0 is 1. Okay, so for the next, at n is equal to 1, 2 plus 1 is 3, so there should be x cubed there. Copy this all over 3 factorial times 4 as it is 4 raised to 1 plus at n is equal to 2 times 2 is 4 plus 1 5, so c5. At c5 there is x raised to 5, and plugging this in for 5 factorial times 4 squared, dot. So simplifying that would give us this plus c1 x plus 4 x cubed over 3 factorial plus x raised to the 5th power 5 factorial plus dot there. So in this we can still simplify it. This is equivalent to CO cosine h 4x, and this is as well plus c1 sine h 4x. So our final answer would be this.